Today on Inevitable, our guest is Mark Lundstrom, founder and CEO at Radia. Radia is developing the world's largest aircraft, the WindRunner, in order to transport offshore wind turbine blades that are up to the length of football fields to onshore wind farms. A potential expansion of onshore wind energy capability that they call GigaWind. And as I learned in our discussion, Radia not only plans to build and operate these WindRunner aircraft, they plan to be a wind energy project developer in order to jumpstart project activity that can take advantage of the GigaWind capabilities they believe they can exclusively bring to market. This is a story of a verticalized go-to-market that is questioning a fundamental constraint of today's wind energy ecosystem, namely the physical constraints of transporting wind turbine blades across the U.S. interstate highway system, and one that is imagining what can be if wind farms could be much bigger than current models and forecasts assume. Rather than me spoil the story further, let's just jump in. From MCJ, I'm Cody Sims, and this is Inevitable. Climate change is inevitable. It's already here. But so are the solutions shaping our future. Join us every week to learn from experts and entrepreneurs about the transition of energy and industry. Mark, welcome to the show.
Thanks, Cody.
We're getting big here today, I think. That's the whole point of this conversation, right?
Yeah, big turbines, big planes, and a great conversation. Looking forward to it.
Let's start with a little bit about how and why you decided to go build giant airplanes to carry giant wind turbines. Where did this idea come from in the first place?
Radia got started about 8 years ago. When we started the company, there was basically a call to action from a couple of the biggest wind turbine companies in the world who are arch rivals, and they basically teamed up and they issued a press release that basically said, our companies and the industry, we know how to make offshore sized wind turbines that are the size of the Eiffel Tower, that have blades that are well over a football field in length, and they're 2 to 3 times as powerful as the turbines that are based onshore. And so there's this frustration in the industry that the industry could make these gigantic machines and distribute them in places like the North Sea, but they can't distribute them where the market is 10 to 20 times bigger in the middle of land masses. This press release, this trade press basically said, can an aerospace entrepreneur or company come and help us fix this logistics challenge and be able to deliver the world's biggest objects to the world's hardest to reach locations?
So it's like a giant public RFP, basically saying, somebody, anyone out there, help us.
More or less, yeah. When arch rivals in a big industry team up together to call out for an industry solution, it's something that an entrepreneur listens to.
You are an aerospace entrepreneur before this?
Yes, I'm an aerospace engineer and then turned into an aerospace entrepreneur and have been building companies for the last 30 years or so. And what I enjoy is bringing aerospace technologies into industries that don't use aerospace and try to shake things up in sort of an unusual way.
Mark, I have to ask a question. I was scouring your background before our conversation, and I saw at a fairly young age, you were on the board of directors of MIT. Can you share a little bit more about that and how that came to be?
Yeah, it's a fantastic experience. And MIT has this wonderful corporate governance structure where they have a fairly sizable board, and they take about 10% of the seats and allocate them to recent graduates. Every year, the 3 most recent years of undergraduate and graduate students, so 6,000 students, elect one person to serve on the MIT board for 5 years as a full board member. So it's a fantastic experience and young in your career to rub elbows with some of the corporate titans in the world.
And you were both a Sloan Business School graduate as well as an undergrad in aerospace and astro engineering, I think is what I saw. Is that right?
Yes, those two, and then also did graduate work at MIT as well, and then some additional grad work over at Oxford.
You say that so lightly, but I think you were a Rhodes Scholar, right?
I was, yeah. That was another fantastic experience.
Congratulations. In the process of you had been trained aerospace engineer, and you'd been building businesses in aerospace, you said in particular, where your goal is to try to bring aerospace solutions to a world that maybe wasn't in the aerospace industry. Tell us a little bit about a couple of the things that you worked on before you decided to do Radia.
So probably the best example of bringing aerospace into an industry that hasn't really used aerospace before was myself and a few MIT friends and professors started a company to basically bring what's called a piezoelectric material into the world of sporting goods. This was the enabling technology to take skis from being straight skis to shaped skis, carved skis. By putting a vibration dampener in there, we were able to reduce the mechanical vibration and enable skis to become shorter and more carved, enabling the curved skis of today.
Kind of like the classic Nike or whomever it was adopting Velcro into a shoe, the ability to take this innovation that was built for, very high-tech use case and turn it into an everyday purpose.
The technology in that case was built for Star Wars, the Ronald Reagan version, not George Lucas, to do space-based satellite dampening. And we figured out how to take that same technology and mass produce vibration dampers for skis.
Oh, very cool. So you saw this press release come out from the major wind energy producers of the world. These would be the turbine blade producers, or would be the actual wind developers, or a little bit of both?
So this was the turbine manufacturers, and it was two of the big ones. And then they, from the beginning, encouraged me to go out and find the other big turbine OEMs and work with them as well, with the vision of creating sort of an industry solution. And so we did just that and have signed up 7 of the top turbine manufacturers in the world that account for about 65% of the world's onshore market share.
This would be like a Siemens or folks like that. Is that kind of the idea?
Yeah.
Maybe walk us through the logistics of wind turbines today. I think we've all seen these fantastical pictures of these semi trucks with these humongous, ginormous wind blades. Those are for onshore. These are the smaller ones, I think. Is that correct?
That's right. Yeah. The blades that you see on the highway, or maybe you get stuck behind them on the highway, are typically 70 to 75 meters in length. And that's really the largest you can transport in the United States. It gets very, very, very difficult as you get beyond that size. And it gets difficult for a number of reasons. They're too long to go around corners. They're too wide to go under bridges. And they're also too wide to go through train tunnels. It's sort of an interesting story how we've gotten into this predicament in society. The dimensionality of roads, road width, so you can trace that back to the Roman Empire. And when the first time that roads were standardized in order to have horses pulling carriages pass each other on the road. And that basically is the same dimensionality that we have today on the highways. And then the bridges, the bridge heights, 16 foot and change. And the reason that is the constraint is that traces back to the 1950s when the United States Department of Defense paid for the highways. They got to decide how tall the bridges had to be. And 16 foot and change happened to be the dimension of a 1950s nuclear missile ICBM on a flatbed. So the dimensionality of wind turbine transport today is basically constrained by horses from the Roman Empire and nuclear missiles from the Cold War.
And these turbines today, are they produced in the US? Like many of them are produced all around the world and then brought here on a boat and then put onto a truck. Is that the way the supply chain works today for onshore wind?
There's a pretty robust domestic manufacturing industry in the United States for wind turbines. And then in addition, you're right, they come in through ports and do a intermodal transfer from the port to a terrestrial vehicle, a truck or a train, and then are moved out to a wind farm. And the typical blade will have approximately 1,000-kilometer journey from either the port or a factory to the wind farm. And so that on that 1,000-kilometer journey, there's, as you can imagine, a lot of bridges, a lot of tunnels, a lot of curves in the road. And so these are the things that are constraining onshore wind.
Then when the semi finally pulls up at the rural location where the farm is, you're actually building some kind of scaffolding crane structure to pull it up way up into the air and stick it into the turbine. Is that right?
Correct, yes. So there's amazing cranes that lift very heavy, awkward objects to very tall hub heights. And it's impressive what they do onshore today. And it's even more impressive seeing those cranes operate offshore. These are gigantic objects that are being hoisted up by these cranes.
Now let's compare this to offshore and the size of the blades there and how that compares to these onshore blades, as well as how these things get way out at sea if they're that much larger.
The offshore turbines are typically manufactured fairly close to a port or within distance to a port where there are no bridges or tunnels. So they tend to be manufactured in fairly expensive locations in a port city or next to a port. The blades will go on a ship out into, for example, the North Sea. And these ships are really amazing. They typically use something called a jackup ship. And these ships are able to pick up the blades at the port, bring them out into the location where the offshore turbine is going to be located. The ship then drops a interesting trellis structure into the seabed to immobilize itself so that it can be stationary, so that it can take a crane and move these objects that weigh 60, 70, 80 tons onto a hub height that might be 140 meters above the sea water. So it's an incredible, incredible process. And by doing that, you're able to have a turbine which is 2 or 3 times the capacity of what we have onshore today. Our goal is to basically do a similar sized machine onshore. And if you can do that, you can double or triple the capacity of the turbine compared to onshore wind today. You can decrease the cost of the electron by a third. You can increase the capacity factor of the utilization by a fifth. And ultimately, you can double the profitability of wind farms. And so this all comes down to a logistics constraint in the end.
And following up from that, are these special purpose ships that are transporting these blades? Did these have to be built special purpose for offshore wind?
Yes, precisely. There is a vibrant industry to make these jackup ships. It's one of the biggest bottlenecks in the offshore wind industry is access to these ships. And it's also one of the most profitable parts of the offshore wind industry are the jackup ships themselves.
And so you said the economics of offshore are, in theory, substantially better, or maybe not even in theory, in reality, substantially better than onshore wind.
It turns out that the economics of offshore wind are actually much more expensive than onshore wind. And so, for example, if you were generating electrons in the North Sea, you might be paying $75 to $85 per megawatt hour for the generation, and then maybe another $10 or so for the subsea transmission. And if you have just today's standard truckable turbines to onshore locations, the numbers are significantly lower than that. So onshore wind is much, much cheaper. And then if you can make the onshore turbines much bigger, similar in size to the offshore turbines, then you're able to take the already cheapest energy in the world with onshore wind and make it 30% cheaper by using offshore sized turbines onshore.
That makes sense. The larger the blade, the cheaper it is to produce energy, except that with offshore, you have all of these additional, very expensive logistics you have to navigate around, including building the platform, transporting everything out at sea, and then getting the electrons through some kind of subsea cable from the platform to the grid.
Yes. And additionally, the turbines themselves have to be engineered in a way that they can be robust against salt water for decades. Maintenance has to happen by boat. So everything is quite a bit more expensive when you do it offshore. That said, they are some of the most amazing engineered products in the world and some of the most incredible wind farms. But if you could take that same size turbine and put it onshore, everything becomes cheaper, everything becomes easier.
I guess all the challenges you just outlined are why, I've seen in the news over the last year and a half, feels like blow after blow of offshore projects being canceled right now. Just in the US alone, we've had projects canceled in New Jersey, Massachusetts, New York. It feels like it's a pretty consistent thing that for those of us following this industry that maybe aren't particularly wind experts, it feels pretty deflating to see.
There's so many hiccups and challenges with offshore wind in general. And what you don't hear about is about all the success stories of onshore wind farm after onshore wind farm being set up without making the news, without making the headlines. Our objective is to take the same simplicity of onshore wind, but take the learnings and the experience of making even bigger turbines and deploy them onshore.
In the US, what percentage of wind roughly is onshore versus offshore? I think it's substantially more onshore. Is that correct?
Oh, yeah, almost all of it is onshore. The offshore industry in the US is just getting started.
Just getting started. And that's where we've seen, unfortunately, these recent project cancellations that are certainly impacting its ability to get wholly off the ground. And it's been larger, you said mostly like North Sea area, for example?
The countries around the North Sea get a significant amount of their country's electricity from the North Sea deployments. The North Sea is a very vibrant place for offshore wind. It works quite well because the seabed is quite shallow. It's really conducive to being able to have offshore turbines. When you get into other parts of the world, it's not as easy to have offshore wind because the seabed is not as shallow, and you start to run into challenges that obviate the possibility of having standard offshore wind. And so then you move into another category, which is floating offshore wind, which is at this point in time, at least, still even more expensive than the standard offshore wind. So if you look at this in terms of a spectrum of cost, floating offshore would be the most expensive, then offshore, and then onshore, and then what we call GigaWind, or offshore-sized turbines deployed onshore, would be the cheapest.
And you mentioned the bulk of generation in the US is onshore. I think the US is the second largest onshore wind generator behind China. Is that right?
It is correct. China, though, dwarfs the rest of the world by far. So the amount of wind deployed in China is impressive. They have, of course, energy of all kinds in high demand in China, whether it's coal or whether it's wind. but they certainly have a lot more wind deployed per year than we do in the United States.
Now, China presumably was not subject to the historical artifacts that restrict logistics in the US, like you mentioned, like the size of bridges due to the transport in the 1950s of an ICBM across the highway system. Has China been able to build these larger blades onshore than the US has?
You're absolutely correct. So, in the Western turbine manufacturing catalog, the biggest blades that are offered are typically in about the 85-meter size. They're not the best selling. The best selling are in the 70-meter range because the big ones, the 85-meter ones, you simply can't get them to most locations. Now, in China, you're right, there aren't as many transportation constraints as we have in the Western world. And so they have blades, onshore blades, that already are in the 90-meter range and prototypes that are just over 100 meters in size. There is a region in China that those 100-meter approximately blades can reach, and the rest of the world simply can't transport that size of a blade to most of the rest of the world.
All the setup there just to help me understand the universe that we live in, which is super helpful. And you mentioned GigaWind, which is, I don't know if you all came up with it, but the name for these offshore sized blades, putting them onshore. You're now designing and building your solution for getting them deployed in the US, which is this enormous aircraft that you're calling WindRunner. Explain a bit more.
So there's two main needs in terms of moving these large turbine blades to onshore locations. There's moving the largest blades that exist today, for example, those 85-meter Western blades that I mentioned, and getting them to most of the places where they can't get to. And then also being able to provide a path for the turbine manufacturers to go all the way up to 105-meter blade. We examined a lot of different ways on how to accomplish this airlift challenge, and then zeroed in many years ago on what we call the WindRunner. The WindRunner will be the largest aircraft in the world by a lot, volumetrically. To give you an idea of how big it is, it's about 12 times the volume of a 747. And so it's a very, very large vehicle, but we've designed it in such a way that it can actually land on relatively short dirt strips, approximately between the dimensionality of two turbines on a wind farm. And so the aircraft will be able to pick up the blades at either a factory or at a port. There's a few ports, it turns out, in each continent that have a port and an airport linked together. And so we're able to do an intermodal transfer and then bring the turbines to an onshore location that might be 1,000 kilometers away from either the port or the factory. In the end, it will be the largest aircraft in the world volumetrically by a lot.
I mean, if these blades themselves are 105 meters, which is larger than a football field, I guess, give or take conversion to yards, these planes are ginormous.
They are. So the aircraft itself, the WindRunner, is 108 meters long. It has a wingspan, though, which is just about identical to an A380. The wing is bigger, so we can fly slower and land slower. And the cockpit, for example, is at about the same eye level as a 5-story building. It is a very large aircraft, but if you put powerful enough engines on a big aircraft, you can do a lot of amazing things. And so we're using some off-the-shelf jet engines that are the same jet engines that power commercial aircraft today. We're just using 4 of them instead of the traditional 2 of them in order to have lots of thrust on the WindRunner.
And just to give people visuals, we're not talking about like a helicopter hoist style transport. We're talking about fully encased, like a cargo plane.
Correct. Yeah. I think one has to put themselves in the mindset more of like a military transport plane instead of a helicopter or a 747. Think of something which is more similar to like a C-5 or a C-17, things that you see in the movies doing delivery of large military cargo. So it's very similar to that, but bigger.
Sounds like you have intentionally designed it such that you can navigate around existing logistics. You mentioned runway. I assume you're going to have to build some kind of special hangar for this thing, presumably. But other than that, the runway itself is not going to have to be part of the economic equation in a major way for the wind farm. You should, in theory, be able to land nearby the farm. Is that correct?
That's correct. Yeah. So we've designed this entire vehicle to be what's called a short takeoff and landing aircraft. And so it lands on a fairly short runway, but it turns out it doesn't have to be a runway. It can be a dirt strip. It's essentially the same surface preparation as you would have on an access road at a wind farm. It just has to be a bit wider and long enough for the aircraft to land. It lands or takes off in only about 10 lengths of the aircraft is what's required for it to take off and land. Now, that said, it's a very long aircraft. So it's about 3,000 feet of actual takeoff and landing space and another 3,000 feet for emergencies, but dirt.
And from there, once you're on the farm construction site itself, presumably you can offboard this onto a semi because it's not having to make these hairpin turns like it might on a road.
Precisely. The engineering, procurement, and construction companies that are responsible for doing the final assembly of the wind farms, they're very confident that once you get the turbine to the perimeter of a wind farm, they can then typically use trucks or these machines called SPMTs that are sort of almost like tanks that move large objects around hard to navigate terrain.
And are you, in theory, the fleet owner of these planes and manage the delivery and logistics services? Or are you selling these planes to project developers or wind turbine blade manufacturers?
On the airplane side, Radia is designing and essentially commissioning the building of these aircraft. We have an aircraft development and manufacturing organization, but we're leaning heavily on the supply chain and companies that have already certified aircraft. And then we will be the owner and operator of this fleet. And the fleet can be used for other applications as well, besides just moving wind turbines, of course, but that's the principal application for the aircraft. And then inside the company, we actually do also have a wind development organization. And so operationally, what Radia does then are really two things. We will deliver big turbines and we will develop big wind farms.
Oh, interesting. You'll be a power developer as well, which I guess can jumpstart the order book for these farms that would require the larger blades.
Precisely. So we'll deliver to our own wind farms. We will also, though, of course, deliver to other wind farms of other companies as well. Our development organization, we do early stage development. Our intent is to bring projects up to notice to proceed and not own and operate the wind farms themselves, but just do the early stage development. And as you said, prepare the order book for GigaWind.
That was going to be one of my next questions, which is how in the world do project developers start to even know this is something they could consider?
So we have already sold one of our early stage projects to one of the larger IPPs and have a few others in negotiations now. We are making sure that the IPPs are well informed about GigaWind and the opportunity that's coming up. Because from their perspective, there's an opportunity to potentially double the profitability of a wind farm. Instead of having a traditional 9% IRR on a wind farm, if you use these bigger turbines, you can get a much, much better IRR in your project economics. And so we're making sure that the IPPs are up to speed about GigaWind. They're becoming our strategic partners. And also there's other important industry segments that need to get up to speed about this as well. And so we're working closely with the hyperscalers to be able to be in a position so that they can use these much larger turbines in their projects. And the other thing that's really interesting about these bigger turbines is they also operate in much lower wind conditions. A typical turbine will require a 7 meter per second average wind speed to have economic viability. But with the bigger turbines, you can drop that down to closer to 5 meters per second. And when you go from a wind speed from 7 meters per second to 5, you basically double or triple the acres in the world where wind can be economically viable. And so it really unlocks a lot of additional real estate. And that's very important in areas of the world like the United States, where we're constrained by transmission and interconnects. So being able to go into other areas of the country, of the world, and be able to do some behind the meter projects in areas that have not been economically viable for wind is also a big deal.
Hey everyone, I'm Yin, a partner at MCJ, here to take a quick minute to tell you about the MCJ Collective membership. Globally, startups are rewriting industries to be cleaner, more profitable, and more secure. And at MCJ, we recognize that a rapidly changing business landscape requires a workforce that can adapt. MCJ Collective is a vetted member network for tech and industry leaders who are building, working for, or advising on solutions that can address the transition of energy and industry. MCJ Collective connects members with one another, with MCJ's portfolio, and our broader network. We do this through a powerful member hub, timely introductions, curated events, and a unique talent matchmaking system and opportunities to learn from peers and podcast guests. We started in 2019 and have grown to thousands of members globally. If you want to learn more, head over to mcj.vc and click the membership tab at the top. Thanks, and enjoy the rest of the show.
Do you expect that siting and permitting for a GigaWind-sized project will be substantially different than a traditional wind farm? These things are already huge, so presumably the additional size may not ultimately impact a lot around the permitting. I'm really curious how you're seeing that potentially play out.
The biggest challenge in the wind industry was when the turbines broke through the 500-foot tip height. Because when you get to 500 feet, that's when the FAA starts to regulate airspace. But already about approximately 40 or 50% of the turbines that are being deployed today have already punctured that 500-foot level. So after that, it's just a matter of degree. It's not a matter of absoluteness. And then you have to make sure that your coordinating with the FAA, with military radar, military flight paths. But one of the really important things about these bigger turbines is on a per gigawatt basis, you need about half as many of them as you do with standard truckable turbines. And so it certainly becomes a bit more challenging in some instances because of the height, but also you have half as many of them. And so that makes it a bit easier.
Do you gain any kind of access to taking over existing interconnect in a way that a traditional wind farm that you said has a larger land area requirement may not have access to? So if you wanted to take over a decommissioned coal plant where you already have interconnect and you can bypass the 7 to 10 year wait period on interconnect because you're taking over land that is already there, does now a potentially smaller area for the deployment of the farm help with that?
The way to think of this is that on a per gigawatt basis, we actually need almost exactly the same number of acres for GigaWind as for standard wind. Now, that said, the amount of power that you're producing from that same acreage is much higher because the capacity factor is much higher. You have the same amount of land for gigawatt, you have half as many turbines, the amount of electricity that you produce is 20% higher. And so on an interconnect basis, it's more justifiable or it's a better return on investment to use GigaWind because you're simply putting a lot more electrons into the grid at that interconnect per year.
That makes sense. So you're not necessarily gaining any kind of land footprint advantage, but you're gaining productivity on the land advantage.
Yes. The use of the land is also less impeded with the bigger turbines because when you have half as many of them, you can just have normal livestock operations, for example, that are less impeded than with standard wind.
So fascinating. I came into the conversation today assuming we were going to talk about all the innovations you're doing around this plane, but in reality, what you're talking about is transforming the domestic wind industry in the US.
We had a study done with Professor Jenkins at Princeton, who's one of the top energy modelers in the country, and gave him the characteristics of the power curves, et cetera, for GigaWind, the economics of it, and asked what would be the results of GigaWind when deployed in the United States. And he concluded that there'd be hundreds of additional gigawatts of wind deployed in the United States. The cost of the electrons will go down by 15%, and the amount of CO2 from the grid will go down by 15 to 30% versus today's truckable technology. And so it's a pretty big step function when you can go to bigger turbines.
And today, wind in the US is, I think, around 10% of power generation. What do the models say and how off do you think they are?
Bloomberg New Energy Finance has a great 2050 study saying, where will our primary energy come from in the decades to come if we're going to come anywhere close to meeting the Paris Accord goals? And they conclude that onshore wind, with or without GigaWind, will be the biggest contributor to our primary power. At that point, we'll have about 20, 25 times as many gigawatts deployed in the world as we do today. There's about $10 trillion of additional CapEx growth that we think is coming in the onshore wind business in the decades to come.
But that's Bloomberg New Energy Finance's forecast. And now you're coming in saying, hey, we're going to improve economics by a substantial amount.
You're absolutely right. If we can reduce the cost of the electrons by a third, perhaps it's even bigger than that, but it's a big enough number to make sure that everybody in the food chain has a very vibrant business.
So now let's get into the realities of what needs to happen to make this happen. Where are you today on the development of WindRunner, the airplane?
It's not a fast process to build the world's largest aircraft. And when one is building a large aircraft, you have to count on it taking oftentimes 5 to 8 years or so. We're more than halfway through that process now. We're finished with all of the main stages of design, meaning we've taken it through things like computational fluid dynamics, finite element modeling, wind tunnel testing, major supplier integration, signed some of the top aerospace suppliers in the world, signed them up at the Farnborough Air Show 2 months ago. And so now, broadly speaking, we're easing into the time where we'll switch into the manufacturing phase by turning on the supply chain and starting to work with some of the top aerospace suppliers in the world. And so we're still a few years away from the first flight, but we've designed the aircraft in a way where it's actually quite a bit simpler. Even though it's very large, it's quite a bit simpler than most aircraft projects because part of the design philosophy and the principles in the beginning was to design what we call the minimum viable aircraft and to maximize the use of the things that are already flying today. And so the aircraft, we've sacrificed dollars per ton mile in exchange for reducing certification cost and risk and schedule risk. And so we've worked with the supply chain to the maximum extent possible, use things that are already flying on mainly Boeing, Airbus, Embraer airplanes, and then repurposing them for the WindRunner.
That's opposed to if you were coming from like a full clean sheet drivetrain, having to get everything certified from the ground up. What I'm hearing you say is, as much as possible, we're trying to use things that already have FAA approval.
That's correct. And that's so important because not only does the aircraft have to have FAA approval, but then the engines and the avionics systems, those also have to be approved. So if you're already using things that are in mass production and already certified, it significantly reduces the cost and schedule risk for bringing an airplane into the market.
Now, I have in the back of my mind that launching a large-scale new airplane into commercial availability is an incredibly expensive endeavor. I mean, obviously from a manufacturing perspective, but just purely from a regulatory perspective. We're talking hundreds of millions of dollars just to get certified. Is that incorrect understanding?
So to certify a large aircraft will require some number of billions of dollars, actually. And so you're right, there's a large capital stack that has to be created for WindRunner to fly. And that's partly what we've been working on for the last handful of years as well. And it turns out that there's quite a number of different important pieces of support for that capital stack. There's export credit agencies that support the aerospace manufacturers in the various countries of supply. There's localized site incentives for doing final assembly at particular locations. There's availability in the United States government, the Department of Energy for certain types of facilities. We also are working on a few pieces of capital stack from the military. There's some pretty interesting military applications for an airplane of this size. And then bringing in some strategic deals with some of the largest companies in the world that are interested in having more green power, whether it's for data centers or whether it's just power into the grid.
Do you have any current GigaBlades on site that you're able to show your team every day and say, this is the thing we got to solve for?
We don't yet.
You can't get them there.
Exactly. The best thing we can do is point to the existence proofs that are well established in the North Sea in terms of the industry's ability to make turbines of this size. But the thing that's important about the onshore version of these turbines is they just have to be much simpler. The capex for the onshore turbines is much lower on a per megawatt basis than it is for offshore turbines. There's great proof points, but today they're in the water.
What does the prototyping process look like for building something like this?
There is no prototyping process. The reason is you prototype something when you want to reduce technical risk. But the way that we've designed this aircraft, there's really not much technical risk in it. It's an execution play. But the technology, as I mentioned, like most of the components, the engines are already flying and the avionics systems, et cetera, these things are already established. And we've designed the airplane around those things that are already established. And so that significantly reduces the technology risk. And so there's really no reason to prototype. The only thing that's really different is the size of the vehicle. It's hard to prototype size without just going for it and making the initial units. That said, we will make 4 initial units that will be used for the certification process with the FAA. I wouldn't consider those prototype units. I'd consider those certification units. And then those units graduate to be operating workhorses once certification is complete.
For you, when you're going out and looking to ultimately raise capital in the business, it sounds like you're needing to prove to someone, hey, we can build this thing, this giant plane. And the reason to do it is because the wind industry can go from X to Y in terms of productivity, price, and everything, which is going to drive demand through the roof. And it's a massively supply constrained market because no one else can deliver this thing other than us. From what I understand it, when supply is constrained and demand is large, you tend to see a high price curve.
This is one of the biggest market opportunities in the world, energy and onshore wind within energy. There's an opportunity to provide the various partners in the food chain an opportunity to double the profitability of the food chain by going to bigger turbines. There's no new technology that has to be developed. We just have to put things together in a different way for this different purpose. And then in the end, back to Professor Jenkins' estimates, should remove 15 to 30% of the CO2 from the grid by making a very profitable business. And so it's something that gets the aerospace supply chain quite motivated and quite excited, because this is an opportunity for the aerospace supply chain to not be part of putting CO2 into the world, but take CO2 out of the world and use an aircraft to actually reduce large percentage points of CO2 from today's grid.
And why wouldn't a large aircraft manufacturer, whether a commercial one like a Boeing or an Airbus, or a military one like a Lockheed, for example, why wouldn't they go after this themselves?
I think most of the aerospace industry is focused on the markets that they've been traditionally focused on: passenger seat miles, defense, space. That's one of the beautiful things about a startup company. You have the flexibility and the adroitness to identify a new market opportunity and go after it. And that's part of the reason why we stayed in stealth mode for the better part of 8 years, is to get a fantastic head start and to develop some very powerful intellectual property around the business.
What made you decide to come out of stealth?
At some point, you need to start engaging a broader array of suppliers and also start to engage a broader array of customers and partners. It was great to be in stealth for a while we were focusing on working with a smaller number of partners. But as we have to start to broaden both the suppliers and the customers and investor landscape, we then decided to come out of stealth for those reasons.
There was a great Wall Street Journal article on you all that came out a couple months ago, I think, that Chase Lockmiller at Crusoe, who introduced the two of us, shared with me, that got me excited to have you on the show and talk. So clearly starting to talk about what you're doing publicly gets other people to want to learn from you and share what you're doing. And hopefully this show and other things like it can reach interested parties like wind project developers who are interested to put some pencil to paper and figure out if something like this might make sense for them. I guess that's the whole domino effect you're going for.
Absolutely. And the reception has been quite amazing. The Wall Street Journal kicked it off, but have been in so many major top publications and news outlets since then. And that certainly has helped generate some excitement in the supply base and with potential customers and partners for sure.
And how have you capitalized the business so far?
So far, over the 8 years of operations, have raised money from a combination of high net worth offices, venture capitalists, large strategic partners in the energy world, and a bit of hedge fund money as well.
Going forward, do you think it continues to be balance sheet capital, or do you raise project financing as needed to start doing actual fab and construction?
Many of the pieces of the capital stack that come from the government are, in fact, project finance structure. And so we think the majority of the capital needed for the project can be raised from project finance type of sources from various governments. In addition, we, of course, have to raise a significant amount of both pure investment money and also strategic deal money. And so we are working right now with some of the top investment banks to go out and raise the next significant round of capital.
What's fascinating about this conversation to me is it's such a good example of when you're in the middle of a paradigm shift, you're shifting from one major system to another, like we are in energy. If you don't stop to think about the constraints that you have in your legacy system, you may lock them into your new system. And if you take a minute to wonder if the constraints of the legacy system should still apply to the new system or not, you maybe can find leaps in innovation. That's what I'm hearing from you today. Hey, we have this highway system that was set up for these various reasons. We're now shifting to a new model of energy that maybe has different requirements. And you wouldn't have thought that the highway transport constraint is impacting our energy economics. But what if we took that away?
When you do take it away, it opens up so many possibilities for so many people and so many industries. With taking away that constraint and enabling WindRunner and enabling these bigger turbines, GigaWind, we'll be able to reach many, many more acres in the developed world and especially also in the developing world. Because if it's challenging to distribute a turbine that has a 70-meter blade in the United States, it's much more difficult to transport even a 40-meter blade in much of the rest of the world. And so in addition to unlocking more acreage in the developed world markets, the emerging economies, we think this will be a fantastic energy source there as well.
For our listeners who are interested, what kind of folks do you want to hear from today?
Anybody who is interested in large wind farms, large powering for large data centers, needs for hyperscalers, large investment opportunities, and people in the aerospace food chain that are not yet in contact with us, those would all be interesting contacts. And of course, hiring fairly aggressively as well. And that's across the different functions of aerospace engineering all the way through to techno-economic modeling for wind farms and wind development and business development. We would welcome discussions with people of all of those different interests.
Geographically, where do you plan to do the construction and fabrication of the aircraft itself?
So the company itself is based in Boulder, Colorado. The manufacturing, though, we've signed an MOU with a major airport and former military base. I haven't announced where that is yet, but it'll be in the United States. And then most of the components of the aircraft actually are being manufactured in Europe. It's a very global supply chain. So, for example, we signed up at the Farnborough Air Show suppliers for the fuselage in Italy, for the wings in Spain, for the landing gear in France. And so these various components will come into the United States. We'll do the assembly and certification of the vehicle in the US.
Mark, what should we have talked about that we haven't hit on?
One of the biggest areas of interest right now in the world of energy, of course, is the power demand that's being generated by AI. I think it's very interesting thinking about how these bigger turbines can impact that voracious need for additional power that really wasn't predicted even 2 or 3 years ago. And so this is going to have huge implications on the grid and interconnects. And so the ability to have these bigger turbines and be able to move into additional acreage around the world, to double or triple the acreage around the world where wind is viable, is really going to help as we essentially bring one India's worth of power generation requirements for AI onto the grid. Being able to reduce the power cost by a third and to be able to double or triple the acres in the world where wind is economically viable is a really big deal when you're talking about the boom of power generation demand from AI and data centers.
Chase from Crusoe and how they're approaching things will likely disagree with this and say, hey, the world is about to shift. But as I understand it today, most data centers are kind of built where there's already expertise in building data centers like Virginia. And then the hyperscaler then goes and buys a PPA, a power purchase agreement for wind or solar or whatever to essentially offset whatever the grid may be that powers that data center. Do you see that shifting? Do you see data centers and the like starting to be built closer to the sources of generation, or do you think it doesn't matter?
I do think that's a trend that I'm starting to see, which is I think the industry used to look at moving the power or the RECs to the data center. Now we're starting to see a little bit more of the data centers moving to where the resource is, where the wind and solar is. And furthermore, I think that as the grid gets increasingly constrained and the interconnects become more challenging, there will start to also be a move to some behind the meter opportunities. And if you're looking at a behind the meter opportunity, you absolutely have to have the data center as proximate as possible to the power generation.
Yes, and I think with AI, particularly for model training, the data center being close to the customers also becomes less relevant because you're running mostly offline batch processes. You don't need to worry as much about latency and getting pixels served up very quickly because you're running these large queries that can take a minute to understand and process itself.
For a large percentage of the AI demand, you just simply need to be where the resource is the best. For the interactive part of AI, you want to be closer for latency reasons, but most of the power gen that's required is for the model learning.
Good last topic to have hit on, and super important when we think about the increasing demand curves around power in the US for sure. Mark, I really appreciate you taking the time to join and share more about what you're building at Radia. And I learned a ton from this conversation. It's definitely went a direction I didn't even anticipate coming into it. So thank you.
Thanks, Cody. A lot of fun.
Inevitable is an MCJ podcast. At MCJ, we back founders driving the transition of energy and industry and solving the inevitable impacts of climate change. If you'd like to learn more about MCJ, visit us at mcj.vc and subscribe to our weekly newsletter at newsletter.mcj.vc. Thanks, and see you next episode.